Welcome back. Today we're doing a deep dive into some foundational experiments in physics. We're looking at Robert Millikan's work.
That's right. Specifically, how he helped pin down two huge concepts. The basic unit of electric charge, the electron, and, well, the very strange nature of light.
And his whole philosophy was interesting too, wasn't it? This idea that science walks forward on 2 feet.
Namely, theory and experiment. Yeah. He wasn't just about ideas. He aimed for what he called crucial experiments.
Experiments that could really settle things, turn theory into solid fact.
Exactly. He wanted proof you could practically see.
Okay, so let's start with that first pillar, the electron. Now, the idea wasn't totally new, right? People have been thinking about electrical particles for ages.
Oh, yeah. Back to Benjamin Franklin, even. Then Weber and G. Johnstone Stoney actually coined the name electron in 1891. And J.J. Thomson had measured the charge-to-mass ratio.
But there was still doubt. Some physicists thought electricity was more like a continuous fluid, not lumpy, like you measure rainfall, but you don't count individual drops kind of thing.
Precisely. So Millikan needed to show, definitively, that charge came in discrete packets. Enter the famous oil drop experiment starting around 1909.
This sounds incredibly challenging.
Yeah.
What was the toughest part of getting that set up right? I mean, to measure something so fundamental.
Just the control needed. He had to isolate the effect of one unit of charge, so he needed incredibly tiny uniform things to carry the charge.
And he landed on oil drops.
Yes, tiny, homogeneous oil droplets, barely 1,000th of a millimeter across, floating in very carefully controlled air between two metal plates.
And then a powerful electric field.
A very strong one, yeah. About 6,000 volts per centimeter. This let him suspend the drops or pull them up against gravity based on their charge.
So you're watching these tiny specks. How did he see the packets of charge?
Well, he could change the charge on a drop, often using X-rays to knock electrons off air molecules, which then stuck to the drop.
Ah, okay. And changing the charge changed how fast the drop moved in the field.
Exactly. More charge meant a stronger electrical pull, changing its speed. And here's the crucial bit.
This is the punchline, right?
This is it. The speed and therefore the force. The charge didn't change smoothly. It jumped. Always by whole number, multiples of a basic unit.
Never by like 1.5 times the basic unit or 2.7.
Never. It was always 1 times the unit or 2 times or 3, like adding identical weights to a scale.
Wow. So that really proved it. The electron wasn't just a useful concept anymore.
Millikan felt it became an experimental fact. He said investigators could literally see the electron through its effects. It was concrete.
And he nailed down the value of that fundamental charge, 8, with amazing precision for the time.
He did. 4.774 times 10 electrostatic units, plus or minus a tiny fraction. It was a landmark measurement.
Okay, so pillar 1. The electron is real, countable. Yep. Check. Now, pillar 2, light. This one's trickier, involving Einstein and quantum ideas.
Right, and this is where theory, that other foot of science, takes a leap. Einstein, building on Planck's quantum idea in 1905, proposed that light itself comes in packets, energy packets.
Light-Quanta, or photons as we now call them.
Exactly, and he came up with the photoelectric equation to describe how these light packets knock electrons out of metals.
So conceptually, what did that equation predict?
Yeah.
Without getting lost in the math.
The key thing was that the energy of the ejected electron, how fast it flies off, should depend only on the light's frequency, its color, basically, not on how bright the light is.
Which is weird, right? You'd intuitively think brighter light means a harder kick.
You would, classically. But Einstein said no. Higher frequency means more energy per packet. Brighter light just means more packets, but each with the same energy for a given color.
And Millikan, he didn't actually like this particle idea for light much, did he?
Not initially, no. He was quite skeptical. But being the rigorous experimentalist he was, he spent 10 years testing Einstein's equation with extreme care.
Trying to disprove it, maybe?
Perhaps, but the irony is, around 1914, his results ended up being the most precise confirmation of Einstein's equation to date. Unexpected, but undeniable.
So his own experiment forced his hand, validating the math, even if the concept of a light particle felt strange.
And it gave the first really accurate value for Planck's constant h derived from photoelectric measurements.
But the particle idea got another boost later, right? With the Compton effect.
Yes, Arthur Compton, 1923. He thought, okay, if light is a particle, what happens if it collides with a free electron, like 2 billiard balls hitting each other?
You'd expect energy and momentum to be conserved. just like with billiard balls.
Exactly. And Compton calculated that the light particle, the X-ray in his experiments, should lose some energy in the collision and bounce off with a longer wavelength, less energy.
A measurable shift.
A measurable shift. And subsequent experiments confirmed it perfectly. They saw the X-rays shifting to longer wavelengths exactly as predicted.
Which really strengthened the case for light behaving like a particle in these interactions.
It demonstrated the fecundity, as Millikan might put it, the fruitfulness of Einstein's hypothesis.
So looking back, Millikan's work gave us these two massive experimental pillars, the discrete electron and the validation of equations describing light's particle-like interactions.
Absolutely. The existence of the electron as a fundamental unit and the mathematical accuracy of the photoelectric equation, those are universally conceded, rock-solid results.
Well, there's always a but in physics, isn't there?
Well, yes. While the equations work beautifully, the underlying concept of light being made of strictly localized particles, these tiny bullets of energy, that's still debated.
Because light also behaves undeniably like a wave, right? Interference, diffraction.
Right.
Those classic wave phenomena haven't gone away.
Exactly. The Compton effect screams particle, but interference patterns scream wave. How can it be both?
So this wave-particle duality, it's still the fundamental puzzle about light.
It remains the all-absorbing uncertainty, as Millikan might have called it. We have these incredibly successful descriptions, but reconciling the particle view with the wave view, that's still the deep challenge.
It makes you wonder then. We have these facts established by crucial experiments, yet the fundamental nature of something as basic as light is still, well, weird. What other established certainties might just be waiting for the next experiment to reveal a whole new layer of complexity we haven't even imagined?
That's the exciting and maybe unsettling thing about science, isn't it? The questions often get deeper, not simpler.